Welcome back, everybody, to Harmonic Analysis Seminar. It's our great pleasure to have Dmitriy Stolyarov from St. Petersburg State University, who is going to talk about Maz'ya's Phi-inequalities. Dima, feel free to start.
Thank you very much for the introduction, and thank you for the invitation. So my talk will be about Maz'ya's Phi-inequalities. That's a new term. And let me first start from something classic. Oh, it works. So these inequalities are some improvements of the classical Hardy-Littlewood Sobolev inequality. So let me first remind you what the Hardy-Littlewood Sobolev inequality is. The main character there is the risk potential. So here is the formula for this operator. It depends on a number alpha, which is between 0 and d, and here d is the dimension. Usually d is larger than 1. However, if you like, you can think about d equals 1 as well. Okay, so this is a little bit complicated formula, but we take Fourier transform, multiply by some function, and then take the inverse Fourier transform. So this is a Fourier multiplier, and its symbol is rotationally symmetric and homogeneous of order negative alpha. So, or it's just psi to the power negative alpha. Well, you can rewrite this operator. A Fourier multiplier is a convolution. However, since this is a homogeneous operator and also rotationally symmetric, you can compute that the kernel of this convolutional operator is homogeneous of order alpha minus d and also rotationally symmetric. Well, you also may wish to compute the constant. I don't wish to do this today, but you can do this. You can express it in terms of gamma function. When an analyst meets an operator, he or she usually asks, when is this operator continuous? And this is given by the classical Hardy-Littlewood Sobolev inequality, okay, for at least these simple spaces LP and LQ, which are somehow what you wish to start from. And it said that the risk potential is bounded as an LP to LQ operator if the parameters satisfy the natural homogeneity condition. I will later, or dimension condition, I will later explain why I give this name to this formula. And also P and Q lie in the reflexive range. I mean, this inequalities. So a natural question, it also has some applications, but I believe that it's worth asking just in itself, under which additional condition does this inequality hold true at the endpoint. Of course, you can prove the weak type bound as usual, but I wish to have the L1 to LQ boundedness under some additional constraints on the function f. Why am I interested in the case p equals 1? So maybe PD people would say that, okay, that's some endpoint. Maybe it's not that necessary because for p equals 1, it might have, okay, let me rewrite this like an inequality because it might have some impact on geometric measure theory. I will, maybe a little bit later, I will comment. So I rewrote the Hardy-Littlewood inequality in this form. And let me talk a little bit about this classical inequality. So this inequality is shift invariant, which is, well, more or less evident because, well, the Fourier multiplier commutes with translations because this is a convolutional operator, and the norms also do commute. What's more, this inequality is dilation invariant. By this, I mean that if we dilate our function, so we consider f at lambda x instead of f at x, then the right-hand side will be multiplied by lambda to the power negative d over p. Then, okay, this is a slightly more involved computation, but the left-hand side will be also multiplied by some power of lambda. If the inequality is true, these powers of lambda should coincide. Otherwise, you can either take small lambda or take very large lambda and get a contradiction. By the way, by this sign, I mean that there exists a constant C, which is independent on F, such that the inequality holds with this constant. Of course, the constant might depend on dimension, on P and Q, but it shouldn't depend on F. And if the two powers of lambda are different, then the constant cannot be independent of F. And from these considerations, you get this homogeneity condition, that the two powers coincide. That's why I call it homogeneity condition. Okay, what about the endpoint case, which I'm interested in? So for the endpoint case, I can compute, since P is 1, from the homogeneity. By the way, do you see my cursor?
Yes, we see your cursor.
Okay, fine, because I will use it. Then Q equals D over D minus alpha just by this formula. That's short computation. And we are working with this inequality and it fails. Why? Mainly because if you have a linear inequality for L1 functions, you should test it against delta measures. That's because delta measures are the extreme points in the ball of the space of measures. And by the way, so for such type inequalities, when you have a convolutional inequality which maps, whose image is a reflexive Banach space, you can always pass from L1 to measures. So here, for these inequalities, it doesn't matter whether we work with L1 or with the space of measures of bounded variation. That's why it's related to some questions on dimension of measures, of maybe rectifiability. So it's related to geometric rectification. Okay, let's return to the counterexample. Why does this inequality fail? As I said, let's plug delta measure. Formally, we cannot do this, but I explained that we can do this. So, okay, if we plug delta measure then into a convolutional operator, we get the kernel. And we've already computed this. It's x to the power alpha minus d. This guy does not belong to the Lebesgue space on the right. You will get exactly the integral x, so value of x to the power negative d. It diverges. Okay, so, but what can be done? Let me start from Galliard and Nuremberg inequality, which is 60 years old, a little bit more. Well, that's not the most common way to write it down. So what is written here? We have some function g, a vectorial function, who is gradient of f. So gradient is a vector, so g is a vectorial function, and you can measure the L1 norm of a vector function. So, and here we have the risk potential applied to g. What I claim is that I1 at g, its LP norm when p is in the reflexive range is comparable to the norm of f. Because this I1 and I1g and f, you can rewrite one in terms of the other with the help of Calderon-Zygmunt operators. And they map LP to LP when p is larger than 1. So here d over d minus 1 is, okay, we need to have d larger or equal than 2. So that's a tricky way to write the Galliard and Nuremberg embedding W11 into LD over d minus 1. On the other hand, this is, okay, it said that the Hardy-Littlewood-Sobolev inequality is true when we have this additional restriction on the function g. Okay, yet another example. It's the Stein-Weiss inequality from 1960, which says that the Hardy-Littlewood-Sobolev inequality at the end point is valid if our function f belongs to the Hardy class. So in their paper, the Hardy class, it was complex Hardy class, which means that the Fourier f is a complex valued function whose Fourier transform belongs to the first, okay, it's supported on this first quadrant or octant. I don't know how you call it in English. I'm sorry. But I believe everyone knows what's the Hardy space. Actually, this inequality, or in modern terms, you can say that for real Hardy class, this inequality is also true. You can prove it, for example, testing it on atoms. Well, this inequality, in fact, has predecessors in the work of Hardy and Littlewood in 1927, when they had D equals 1, H1 the complex space, and alpha equals 1/2. And of course, they worked with Fourier series instead of Fourier transform. Okay, that's classical examples. Now let's go to a more modern one, which can be found in the work of Burgundy and Bridges around 2004. So now G is again a vector field, so the vectorial function, and we also require that it's divergence free. If it's divergence free, then we get the Hardy-Littlewood subleaf inequality. Actually, the story is a little bit, as usual, a little bit more complicated. So first, Burgundy, Bridges, and Mironescu proved this for the case when G is a special measure on a curve, which is divergence free. And then slightly later, Burgundy and Bridges used this inequality together with something called Smirnov decomposition theorem to decompose general G into these special vector fields. Okay, so these three examples say that these three conditions somehow forbid substitution of a delta measure into these inequalities in the Hardy-Littlewood subleaf inequality. Well, the later work of Burgundy and Bridges gave rise to a very rich development and very rapid. I would say in 10 years, there were very many new inequalities obtained by many famous people, also by Burgundy, by Stein and Lazzani, by Maz'ya and others. However, I'm sorry, I will skip all this development because we don't have much time, and go to a next milestone, theorem by Jean von Schafften. So what he did, he said, okay, let's now replace divergence with arbitrary differential operator. So somehow he described the restrictions, the differential restrictions, which improve, which somehow correct the Hardy-Littlewood subleaf inequality at the end point. So here G is some vectorial function and A is homogeneous of some high order or maybe low order elliptic differential operator. Well, here I should have explained what an elliptic operator, elliptic vectorial operator is, but this will take much time, and more or less there is a unique natural definition. So when does this inequality hold true? Exactly when you cannot plug delta measure into it. So there is a small problem because you need to explain what a delta measure is. We have vectorial measures. That means exactly that we have delta measure tensor to some vector. So if you cannot plug this into this delta measures into this equation, then the Hardy-Littlewood subleaf inequality holds true. Okay. What I want to say is that the differential operators are somehow not the gist of this problem. So this holds in a large generality. So let me state my theorem. So suppose we have some closed linear subspace of the dual Schwartz class of some vectorial distributions that's invariant under translations and dilations. By the way, in von Schaftingen's theorem, we needed to have our operator homogeneous to have this dilation invariance. It's very important in this business. And also, let's suppose we have some alpha, then this inequality, the Hardy-Littlewood subleaf inequality, holds true for functions f in W, if and only if this space does not contain delta measures. So this theorem is more general than the first theorem, and also there is, like, you know, some sport achievement that you can slightly improve the space on the left. There were several conjectures in this field whether you can improve the Lebesgue space to a strictly smaller Lorentz space, and well, you can. Okay, but that's not what I was going to talk about today, though I must explain what are, so these inequalities are usually called Burgundy Bridges inequalities. And in around 2010, actually the paper was from 2010, Maz'ya conjectured another way to correct this Hardy-Littlewood-Sobolev inequality. So in all previous inequalities, the philosophy was that the Hardy-Littlewood-Sobolev inequality holds true as long as you can plug their delta measures. So he found a way to correct the inequality in such a manner that you are allowed to plug delta measures. Of course, when you gain something, you need to lose something, and yes, we are losing linearity. So these inequalities will be non-linear. So here his conjecture is, it's a little bit heavy, but let me explain who is who here. Let's first take a look at the inequality. We have some function f, which is sufficiently smooth. Oh, I'm sorry, we don't need this second condition about mean zero. Forget about it. So this is some regularity condition. It's also not of crucial importance. We take its Laplacian and also consider its gradient on the left. So gradient is operator of the first order, Laplacian is operator of the second order. So there is a formula in the style of risk potential, slightly different, with which you can represent the gradient in terms of Laplacian. So it's Laplacian f convolved with something, and this something had the same homogeneity as risk potential of order 1. So what we have on the left is somehow like L1 norm of G. What do we have on the right? We have some function phi. So we know that this inequality, if we have Laplacian here, somehow you can plug delta measure into it. So we cannot have the LQ or LP norm. The idea is to replace it with an expression that has the same homogeneity property, but has additional cancellations. So for that, we pick some function phi, which maps RD into R, and let it be positively d over d minus 1 homogeneous. So we replace the function absolute value of t to the power d over d minus 1 by some other function that, by the way, is defined on vectors on RD. And let it be also locally Lipschitz, just to have some regularity. So this inequality holds true with the uniform constant if and only if phi satisfies, as we will see later, a natural cancellation condition. By the way, feel free to ask questions. Okay, so that's a conjecture, and instead of proving it, let's first generalize it a bit. First, here's the formula I was speaking about, so which represent gradient f in terms of the Laplacian. So here is this kernel. By the way, it's vectorial, so it's y over absolute value of y to the power d. And again, I'm lazy to compute the constant. Let's replace this formula with a more general one. So let k tilde be some function that maps the unit sphere into some vector space. And it generates the kernel, which is homogeneous of order alpha minus d, in a very natural way. So when you have x, to define the value of k at x, you take its, okay, I think it's clear it's homogeneous, right? So here x over absolute value of x belongs to the unit sphere. You apply k tilde to it, and also you need to multiply by absolute value of x to the right power. Okay, so let's also pick p, which is d over d minus alpha, and take this function phi to be positive. By the way, by positively p homogeneous, I mean that phi at tx is t to the power p phi at x, and t is non-negative. So for example, it's not necessarily symmetrical. Okay, so the question is, when does this inequality hold true? So what do we have here? Exactly what Maz'ya asked, but we have a more general kernel. We wish to have some freedom with the kernel. Okay, let's now so what's important here that unlike the hard-edged Sobolev inequality, this k tilde might be important. So for LP norms, there's the rich theory of Fourier multipliers or Calderon-Zygmunt operators, which says that as long as k tilde is sufficiently smooth, it doesn't matter. Here it matters, as we will see. Okay, let's try to find some necessary conditions for this inequality. Well, necessary conditions. Again, we have certain, okay, this is a non-linear inequality, as you might see, but by the way, why do I call it phi inequalities? Because in probability, sometimes when you cannot estimate the, say, the p moment, you replace it with some function phi and call this phi inequality. It's an interesting story, but Maz'ya himself, after I proved the conjecture, we talked a little bit, and he said that he never knew about this, but for some reason, he has chosen the function phi. So that's, I mean, that maybe that's not accidental. Okay, maybe not. Okay, so let's return to mathematics and let's try to plug delta measure. Of course, we will have something like 1 on the right. What will we have on the left? Well, again, it's pleasant to convolve delta measures with functions because we have the function itself. And let's rewrite this integral on the left. We can use the polar change of variables and rewrite, also use the formula for k tilde. So here, this comes from the polar change of variable. We integrate over the sphere, and then with respect to the radius. Now we use the homogeneity property of phi. And also you see our homogeneity relation that links P to D. So here I rewrote it in convenient manner. So we have here alpha minus D times P. We've used that phi is P homogeneous. So we get D and it cancels with this D. Oops, we have a divergent integral. So the only way for this to be 0, or at least to be bounded, is that this inner integral is 0. So here is the cancellation condition. Of course, this plugin of delta measure is not rigorous, but you can make it rigorous. So why do we have plus and minus here? Because if you plug negative delta measure, then you get minus here. In Maz'ya's conjecture, he had symmetric kernel k tilde, and that's why you can use the symmetry of the sphere. Here we don't necessarily have it, so we have somehow like 2 cancellation conditions. Okay, so here's the theorem, which says that this necessary condition is also sufficient. Here we also, let's go through this theorem again. So we have the function phi, which measures vectors, and we have a kernel that maps the real line to vectorial functions. We also have the homogeneity condition. And then we say that this inequality holds true. We need some regularity requirement. So the function is smooth and has mean 0. These are technical requirements. Why do we need them? Because if we don't impose something like this, if we take arbitrary functions f, then the value on the left might be simply undefined as a Lebesgue integral. So whenever, in any reasonable way, when you regularize it in any reasonable way, you will get 0, but without this, it will be simply divergent. So we need some assumptions of this type. So this is for regularity around 0 in a sense, and the second is for regularity at infinity. So this inequality holds true with a uniform constant, if and only if we have the cancellation condition. So that's the theorem.
One question.
Yes.
L and D are different, right? They don't have
right. They are not necessarily one and the same here.
And the constant, it depends on D, L.
Of course, and also on the function phi.
Okay.
Yes. So here, yes, I think it depends. No, it's not about dimension-free estimates. I'm sorry, we are not on that level. Okay, an example. I must give an example. Actually, this He's not very rich with examples. However, I've already gave a talk about this, and PD people say that, okay, there will be more examples. However, let me give one example. So let D be equal 2, alpha be equal 1. So we're trying to restore an integer derivative. And let's take the simplest possible kernel, like in Maz'ya's conjecture. Also, let's take some specific function phi. Actually, this is not one function, but a class of functions which are simply quadratic functions. So here zeta belongs to the circumference. So then we, using this formula which restores the gradient from the Laplacian, we get such type inequality, right? So we apply it to Laplacian, not to the function f itself, but to Laplacian f. When we use this curve, we get the gradient. And so here is our inequality. When does it hold true? We need to check the cancellation condition. So it will be integral of phi over the unit sphere, okay, unit circle. So when you integrate zeta 1, zeta 2 over the unit circle, you get 0, right? This function is, okay, it's odd with respect to zeta 1. And the integrals of zeta 1 squared and zeta 2 squared, they are equal, right? So you get a11 plus a22 equals 0. So when this is true, the inequality on the top is also true. Actually, that's not my inequality. It was obtained by Maz'ya and Schafften in 2008 and served as the main inspiration for Maz'ya's conjecture. So you can give it to, okay, maybe you shouldn't give it to students in your Fourier analysis class, but it's okay, you shouldn't, but this is just accurate plate with the Fourier transform. Okay, so what's I won't be able to survey the whole proof, but I will try. First, I wish to describe where does the idea come from. So in harmonic analysis, it's quite often that you try to model your problem with some discrete things. Usually that's problems about Martingale. So for example, you model
Dima, can I ask, can you go back to the statement of the theorem again?
Yes, sure. Here it is.
So it's if and only if condition. Okay.
Right.
And the example you showed, do you have some other classical examples you can recover using your theorem?
Yes, they are a little bit lengthier than this one. For example, let's take a look at the theorem. You can take d equals 1, where it is. So d equals 1, L equals 1, and the kernel alpha equals 1/2. So you have, and k of zeta is also zeta. Then if you take, then phi is a function on the line,
yeah,
which is positively too homogeneous. If you take the function x, absolute value of x, then it satisfies this cancellation condition. You can write the inequality, but it will be, well, okay, it will take not the whole slide, but maybe 2 lines. So there are other examples, but since this conjecture is just conjecture in itself, I don't know where these examples are really important or no. So people say that this might be somehow helpful. Let's see. Let's give it some time. Okay, so what about differential operators and how to model differential operators with martingales? Because usually we'll find analogs for Calderon-Zygmunt operators. Here, it's somehow important that we have, okay, not differential structure, but anyway, we have operators of fractional order. And the answer, an unexpected answer, can be found in the work of Svante Jansson from 1977. And he had operators which are very close to martingale transforms, which what we now call martingale transforms. For those who like inequalities for martingales, you can say that the Janssens operators are particular cases of Gandhi operators. However, the special cases is very nice. I will try to survey it in a couple of slides. So now I will speak a little bit on discrete. So by the way, I have about an hour, a little bit less, I believe, right?
Yes, you can speak right up till 12, definitely.
Okay. So we wish to so now I will speak a little bit about these discrete versions, discrete martingales, and then try to convince you that this has some relation to the proof of the original conjecture. Okay, let me recall what a martingale is. I will need very special martingales, and what I'm saying now is completely non-pedagogical. You shouldn't teach martingales in this way. On the other hand, we don't have much time. So let Fn be a partition of the unit interval into m to the power n intervals of length m to the power negative n. It's clear what it is. So it's enumerated with n, and here m is some fixed number, say m equals 2 or 3. We call the sequence of partitions the filtration. So I will show a picture a little bit later. So suppose we also have a summable function, which I call phi of phi infinity on this interval. And we define a sequence of functions phi n. These functions are piecewise constant. And for any interval of nth partition, we just define them to be the average of our function phi. Okay, then this sequence is called the martingale. Okay, so here is an example. So this is 0, this is 1, and we have the absolute value function. That's absolute value of x minus 1/2. So I will have m equals 3. However, when n equals 0, there is only one interval in my partition. So just 0, 1. So phi 0 would be just the average. Okay, here it is. Now I pass to the partition F1. So it has 3 intervals, as I said, m equals 3. On each of these intervals, I should compute the average. So my second function, phi1, is a function with three steps. And they are just the averages of this function phi infinity. Well, I can go further and split into 9 intervals and compute the average on each of them. And here I get the blue function, which is phi 3. So what you can see, why do I call phi infinity? Because when n goes to infinity, this phi n converge to phi in some sense. So you may think of a martingale as of a way to approximate some function. Actually, that's not true, because usually they call a martingale just the sequence, and it does not necessarily approximate the function phi infinity. I mean, the function phi infinity does not necessarily exist. Okay, let's now return to our differential operators, something like this. So we need to consider Martingale differences. It's just difference of 2 consecutive steps of Martingale. And so how does this function look like? It's constant on each small interval, I mean interval in Fn plus 1, and has mean 0 on the intervals of Fn, on large intervals. So we will identify the vector d phi n restricted to W, where W is an atom, is a lone interval, an atom in Fn with a vector in Rm. So it's just a string of m numbers, right? You need to specify this the way you identify, but okay, let's assume we have specified. Consider some linear operator that maps Rm.
Dima, 1 second. W is from Fn or Fn plus 1? Because
Fn.
But it's a function on each interval, right? It's not constant on W. This dphi is not.
Yes, it's not constant on W. So on
okay.
W, you have m numbers. You have piecewise
Right.
constant
Yes, okay.
constant with m values.
Okay, m values. Okay, that's
yes.
why RM. Okay.
So you need to keep track of this. For
the
example,
average zero of these numbers, right?
Yes, it's important that the average is 0. However, as you might see here, I neglected somehow. So assume we have a fixed linear transformation from Rm to Rm tensor something. So then, there is a terrible formula. So let me explain what happens. You pick an atom. You pick n, then you pick an atom in Fn. So on this atom, you have your small part of Martingale difference, which is, as I said, a string of m numbers. You treat this string of m numbers as an element in Rm. You apply t to it and get a string of m vectors in Rl. Then you think that this is a new Martingale difference of someone. Of course, here you need to ask that you have mean value 0 here and mean value 0 here, but for the sake of simple notation, let's forget about this. Then you multiply by characteristic function of omega, sum over all atoms over all intervals of nth partition, and also multiply by m to some power negative alpha n. So these are Janssen's transforms. They're slightly more different because usually for Burkholder Martingale transfers, you just multiply by constant here. You do not apply linear operator. So this is a little bit more general. So, and this serves as a good model of our operator K tilde F, as it appears somehow. So when you have a Calderon-Zygmunt operator, you don't need this mixing. However, to model these operators, you need this to mix them a little bit. Well, so there is a natural. So as we said, our operators were translation invariant and dilation invariant. So this sum is for translation invariance, and this parameter m to the power negative alpha n is somehow corresponds to dilation invariance. Okay, let alpha be 1 minus 1 over p. So this is natural homogeneity condition, as we had previously. Then the cancellation condition on phi reads as follows. So if you remember how we got the cancellation condition, we plugged delta measure. So in this world of martingales, also delta measures exist. You just take phi at infinity equal to delta at x and run this procedure with martingale. And from this, you get this cancellation condition. You can plug it into, okay, I haven't written the inequality, but that you can find a good analog for cancellation condition. So the vectors v, these Martingale differences, which correspond to delta measure, are just m minus 1, negative 1, and so forth. And you can place this m minus 1 in any place in the screen. So that's the cancellation condition. Here's the theorem that if we have mild structural assumptions on T, I don't know whether they are necessary or not, then this inequality, which is a direct analog of Maz'ya's inequality, so we have L1 norm on the right raised to the power P, and also mathematical expectation, or the integral of phi evaluated at F convolved with K. This inequality holds true for all simple martingales with a uniform constant. So the word simple means that the martingale stops after n steps, and this corresponds to considering smooth functions f in the initial conjecture. So you need some structural assumption, some regularity assumption. So if and only if T satisfied the cancellation condition I wrote on the previous slide. So that's a direct analog. Why do I like it? Because in this world of discrete martingales, whenever for some class of problems, whenever you have an inequality, it corresponds to a certain monotonicity formula, which is usually generated by an object called the Bellman function. I won't be able to speak long about this. But I would say that this problem is amenable to something called the Bellman-Burkholder method, or this is just a fancy way to run induction on scales. But in this world, if the inequality holds true, there must be a good Bellman function. So that's why this inequality is somehow easier to prove, because there is no other way other to find a good Montanistic formula. So for this problem, here is the process which will be a super Martingale. So here the first term is something we have on the left, okay, without absolute value, but you can estimate a mathematical expectation of phi and negative mathematical expectation of phi. The third term is something we have on the right. However, when you start working with this Bellman function problem, you see that there must be a certain intermediate term that links them. And I call it MP of two arguments. And this terrible creature, you see, it depends on n, it will be a super Martingale. So for those who like PDEs, super Martingale in the probability length is probability for Montanistic formula. So who is the function MP? This is a very simple function, which is here everything should be positively P homogeneous. So it is P homogeneous, and it's a little bit tricky, just a little bit. So this will not work if you take just one of these terms, x, y to the power P minus 1, or vice versa. It works only with this function minimum. Okay, so that's all I wanted to say about the Martingale problem. I think I have about 20 minutes, maybe a little bit less. And let me return to the original Euclidean problem. So since we had Martingale, let's split our kernel K into dyadic parts. So from this, we get the kernels Kn at x. So it's just a part of K. And I will also have this notation K less or equal than n for sums. So this is something like 1/2 of the kernel. Let me draw the picture. So assuming this is our kernel K, actually this is the graph of x, absolute value of x to the power negative 0.8 or something like this. So who is Kn? Just the part of the kernel from 1 to 2. It's K minus 1, and also it's symmetric 1. So for larger dimensions, it will be a function on a ring. And K negative, K less or equal than n is the part of the kernel that starts from absolute value of x equals 1. So this is a bounded function. Okay, so you can restore the kernel from these parts, and also these parts are self-similar somehow. So you can, if you have K0, then you can compute all the other parts by this simple homogeneity relation. So if we return to Martingales, then this K less or equal than n somehow corresponds to the Martingale, and Kn corresponds to a Martingale difference. Okay, so let's make the first step. Since our problem was translation and dilation invariant, we may assume that the support, so our function is completely supported, we may assume that its support belongs to the unit ball centered at 0. Okay, and now we can split our expression into parts using telescoping summation. So what do I have here? I say that my K convolved with n is K less or equal than some large number convolved with f. Since my function f is sufficiently regular, you can pass to the limit, and then I simply do telescopic summation till level 0. So why do I stop at 0? Because I have this assumption that my function is 0 outside the unit ball. Because I have a lemma, which looks like very classical. I haven't found it in the literature, but I believe it is somewhere there, that if your function is supported in the unit ball and has 0 integral, that the only place where we will use this condition, then you have this estimate. You can estimate the first term in terms of the right-hand side of my initial inequality. How you do this is...
There is no any assumption on K in this lemma, or it has to be the same?
It has to be the same. So we had this assumption on K tilde that K is homogeneous of order alpha minus D. You don't need the cancellation condition for K here, of course, simply because it involves function phi. So yes, it's just locally Lipschitz kernel that's homogeneous of order alpha minus D, and it is bounded, so it's K less or equal than 0. So it's just how you prove it. You simply subtract this mean of f, and this expression, if you don't have this condition, then it decays absolute value of x to the power alpha minus D, and with this condition you get some additional power of x and you win. Okay, so let's recall our favorite function MP, which is very important in this business. So what distinguishes it from these two other functions, which are natural, is that this function is locally Lipschitz. These two guys are not, and it's important for this Bellman induction. The next lemma allows us to split further. If you remember, this was the term we needed to estimate on the left-hand side. You can go further. So this is something like phi at Martingale, at phi n, fn. Now you can estimate it by the mean of the Martingale difference of phi and also the additional term. So that's something like we had in the Martingale world. So this lemma again, and you need to use that p is less or equal than 2 here. For p larger than 2, you need to plug slightly different function MP. I won't speak about this because for in initial Maz'ya's conjecture, p is d over d minus 1. So for interesting cases, it's less or equal than 2. So this lemma, I won't be able to prove it, but this is just accurate work with this integrals and function phi. So it's lemma about numbers. It's not about some tricky operators. Yes, so I'm sorry, let me go back. So now we need to estimate the sum of first terms with respect to n and the sum of second terms with respect to n. So theorem for the first terms, you need to prove this, estimate, and also you need to prove the second estimate. So the first estimate is natural when you work with Hardy-Littlewood-Sobolev inequalities. If we had the LP norm here instead of this phi modification, then this creature would be this norm as this Besov space. For those who like Besov spaces, for those who dislike, you can write this in a simple way. So, and by the way, so with Hardy-Littlewood-Sobolev inequalities, with this Burgundy Bridges inequalities, their improvements to the Besov scale are true. So that's why we think that maybe we can prove it in this phi world as well. So what I wish to do in the remaining 10 minutes, I wish to give a hint to the proof of theorem 1. And so theorem 2 is also interesting, but of course I don't have time for this. So it simplifies when p equals 2. And the proof is close to being straightforward. The proof for p less than 2 relies upon something called the three-lattice theorem. That's a usual instrument when you transfer Martingale problems to the Euclidean setting. But let's return to theorem 1. First, we need to start with some local bound. We have already localized with respect to n. Now we need to localize with respect to the space. Well, suppose that we have a completely supported function, then we have this estimate. Let me speak a little bit about it. So first, it's about k0, not about kn, but we will be able to use dilation invariance and prove a similar lemma for when we have kn. What do we have on the right? We have the L1 norm raised to the power p minus 1 and something like L1 norm raised to the power 1. So this expression is something like the p norm of the L1 norm. However, sometimes it's smaller. When? So recall that K0 is a kernel that is bounded and is supported on, okay, ball of radius 2 around 0. So maybe you can split F into parts which are supported on balls of radius 1 or cubes of radius 1, because this operator is somehow localized to the scale 1. Imagine that F is supported on a cube of radius 1 or ball of radius 1. Then this expression on the right is strictly smaller than L1 norm. So for some functions, it's close to L1 norm, but for our main enemies, which are delta measures, it's 0. So this lemma improves for delta measures and also for very well localized functions. Okay, so how do we prove it? And this lemma is the core of the whole business. So we will be using this elementary inequality. So, okay, where does it come from? Recall that phi is P homogeneous, so you may divide over this maximum. And then this is simply that this function phi is locally different. Okay, so let me rewrite it. And I have a long chain of inequalities. Let me go through it briefly without going into very much into details. So here I use my cancellation condition. I need to use it somewhere. So if you remember, K0 was a part of K, and my cancellation condition was imposed on the function K tilde. So I wish to say that the integral of the second term is 0. So integral f is constant. Here, integral f is not necessarily 0. And so, so I subtract 0, as they usually do, for example, in Calderon-Zygmunt theory, to catch the cancellation. Then I use this inequality. Now I have to estimate the difference between between the convolution and this thing. You interchange the order of integration, use that this kernel K0, it has bounded variation to obtain the second bound. So I wish to say that this, okay, maybe it's difficult to follow all these inequalities. I'm sorry. But what I wish to say that this main lemma where you use the cancellation is very close to what you can find in the literature about Calderon-Zygmunt operators. Okay, now how I will be using my lemma. I split my space into integer cubes. So it's just cubes generated by integer lattice. And I will apply my lemma to the functions. Oh, I'm sorry. Fj, which are just f times characteristic function of a cube. When I apply, okay, I get the expressions on the right. Of course, the problem is that I have phi here. You need to somehow to be able to split. So this is the derivation of theorem from lemma. It's not just like for LP norms, you would use like triangle inequality here. You can't use triangle inequality. So it's a little bit tricky. That's why you get larger cubes here. And this will cause some mild problems later. So we will need to use this 3-lattice theorem. However, you can estimate the integral on the left by some improvement to the L1. So, well, you can use dilations and prove a similar inequality for arbitrary n instead of K0. And you will get additional factor 2 to the power n here. Okay, so now let me end the proof for case p equals 2. Then this power of the L1 norm here is 1, and you can use a simple estimate like this. So instead of product of 2 integrals, you have a double integral. How do you prove this? Well, you can integrate with respect to y first, and say that for any fixed x, you can replace y with this infimum. Then integral with respect to f with respect to y will be the first integral, and the integral with respect to x will be the second integral. Okay, so now we have to compute the sum with respect to n, and we get this. You remember there was an additional factor. And so, because these cubes, Q and J times Q and J, they lie in this set, they somehow cover it. And therefore, if you prove that, okay, we have integral absolute value of f, absolute value of f. If we prove that this something that does not depend on f is uniformly bounded, then you have integral of f times integral of f, which is your desired right-hand side. So you only need to prove that this series converges. Well, and I've drawn the picture for d equals 1, and you see that at each point, when you sum these functions, you get geometric series. For example, for point 1, you have 1, 1/2, 1/4, and so forth. And so it sums to 2. Well, non-integer points, the sum will be slightly different, but anyway, this is uniformly bound. Well, I'm sorry for too many inequalities for one talk. Thank you for your attention.
Thank you very much, Dima. That was a perfect talk. And congratulations on solving Maz'ya's conjecture. I have some questions. Why Janssen was interested in his operator? What was his motivation?
Yes, let me return to Janssen. So there is some. Unfortunately, I'm not using a tablet, but so I cannot draw. He was interested in something called later called the Okiyama Theory. So you know you have the Pfefferman-Stein theorem that for H1, the function f belongs to H1 if and only if the Riesz transform evaluated at f belong to L1, and also the function itself belongs to L1. And he wished to characterize the operators you wish to replace the collection of Riesz transforms and the identical operator with some other Calderon-Zygmunt operators. What are the necessary and sufficient conditions for this collection of Calderon-Zygmunt operators that for them to define H1? So he was trying to prove this, so he was a student of Carlisson, and if I'm not mistaken, I hope, and he constructed this model. And for this discrete model, he managed to solve the problem and found the necessary condition. And sufficient condition was found a little bit later in 1981 by Japanese mathematician Okiyama, and that was an active paper then. It's a little bit complicated, but somehow you need to dualize Janssen argument. So Janssen argument is for L1, H1, and this argument by Okiyama is for BMO and L infinity. And it, especially for 1981, it's complicated. So that was a problem of translation.
I see. Another thing, Martingale Inequality that you wrote, is there continuous version of it for continuous Brownian no stopping time? Is there something popular in probability that people already?
Yes. So this is a very good question, but I believe you know these things better than I do. So I'm not that very familiar with the Brownian motions. My immediate answer would be, I would say I don't know. So of course there are versions of the Hardy-Littlewood inequality, for example, for semi-groups of operators, and of course for Brownian motion. But here it seemed that this discrete structure is important. Maybe that's because our tools work like this. So of course it's natural question, because it's simpler to derive inequalities in Euclidean setting. For example, you wish to plug Brownian motion into your Bellman function and say, aha, it works. It seems that here there are some difficulties with this approach. That's only what I can say. Maybe it's simply, for me, it's more convenient just to rewrite the proof using discrete using inequalities for convolutions rather than try to plug Brownian motion. If you could say something, I would be interested to learn.
Okay. And a last question, can you prove Burgundy Bridges using this Martingale arguments?
Yes. So if we return to this theorem here. Sorry. Yes, this one. Actually, this is a beast. So the proof is 40 pages long, and I know only 2 persons who read it, except me, of course. And well, though it seems people were interested in it, because this question about this one here, and also about actually, it also serves several conjectures in the field, one by Burgundy Bridges themselves. And here you also state a martingale problem, and it's quite well. After you state it, you will prove it in a while, even without Bellman functions. You can write a Bellman function, but you don't need. You just need to consider 2 cases and do something like induction in this case. However, the translation for these more general spaces is horrible. So yes, you need to use some forms of, well, I call it Bennett-Kerber-Tau inequalities, but you would like the name Brest-complete more. So instead of some simple dimension estimates, you use some tricky Brest-complete inequalities. And also there are lots of this, like in how you call it, Cottin-Schwarz tails, and also some maximal functions involved. And I mean, this is difficult. You can prove, but here maybe it's better to find a good Brownian motion.
Okay, can you say again? You can use Brest-complete to in the proof of
You are somehow forced to use something like Brest-complete to estimate dimension. So instead of, so here the martingale is generated by convolutions with heat kernel, by heat extensions. And there are 2 estimates. Either, well, I mean, it actually, it's a topic for a separate talk. Yes, I would say so. Maybe, if you wish, maybe we can talk in person, because yes, there is something like Brest-complete inequalities inside, but simple Brest-complete. Okay. From the point of Brest-complete inequalities, there are not that many, like, in Brest-complete inequalities, you usually have projections or this matrix. So the matrix is simple, but the inequality itself is, well, you need weighted versions. So maybe it's not that interesting from the point of view of Brest-complete inequalities, but because it's an instrument there. But, well, you need to use some additional things. Something like tangent measures. I mean, it's fairly long, but you can prove it using something like Martin.
One remark I want to say, maybe you know this, in Hardy-Littlewood-Sobolev inequality, there are also sharp constants known.
Oh, yeah.
They are important because when P goes to Q, you get equality and you can differentiate. And when you differentiate, you get log-Sobolev inequality, which Beckner at that time used it to prove that log-Sobolev inequality to solve Stein's conjecture on hypercontractivity for the Poisson semigroup. Okay, I'm not saying that if there is any chance to get sharp constant, but maybe when D goes, okay, D is discrete, right? Okay, you cannot recover, if you had some sharp constant, you would not recover some equality case. Maybe you want more parameters.
Well, maybe you can try to send alpha to 1. Right,
alpha
this corresponds
yes.
to having Q equals 1, and you have also something like entropy estimates there.
Yes,
but of course, okay, it's not about sharp constant. The level of development of the field is very far from it. That's what my feeling is. Maybe I'm mistaken, but
okay. Yes. Any other questions from the audience? Okay, if there are no questions, let's thank speaker again, and I will stop recording.